Hi everyone, I'm ECG from FKE UTHM. Today we'll be looking at the derivations of capacitance of coaxial capacitor.
Alright, now let's look at the second type of capacitor, that is the coaxial capacitors. So basically, what is the coaxials? Okay, so coaxials, the structure of the coaxial is something like this. So it has an inner conductor, okay, inner conductor, and also outer conductor, okay, outer conductor. So this is the outer conductor of a coaxial line, okay. So it has inner and outer, okay. So this is the outer, okay, and this one is the inner. And in between the inner and outer, okay, we have a dielectric, okay, we have a dielectric. So the dielectric can be any material or can be a material. So this is a top view, okay, this is a top view, okay, of a coaxial capacitor. If you want to look at the side view, okay, we can look at the side view. So this is a side view. So you have a inner conductors, okay, you have an inner conductor, then you have outer conductor. No, this is still inner, okay, then you have a line, so this is inner, so inner conductor, and you have outer conductors, okay, outer conductor. Okay, so this is the coaxial line, okay, so you have inner, okay, and you have the outer, okay. So you just imagine the inner of the outer conductor, the inner of the capacitor, okay, is connected to the negative terminal of a DC source, okay. So as the result, all the negative charges, they are accumulated, okay, on the surface of the inner conductors, and the outer conductor is connected to the positive terminal of the DC voltage, okay. So all the positive charge, okay, is on the surface of the outer conductor, okay. So you can see from the top view, so this is the negative charge, and here you have a positive charge, okay. So the electric field, okay, will be from positive charge, okay, towards to the negative charge, okay. So this is the electric flux, okay, in between these two conductor, inner and outer, okay, inner and outer. So now let's define the capacitance of this coaxial conductor, coaxial capacitor. So the formula is this one, okay, Q over V. So this formula is the same as the parallel plate capacitors, okay. So we are going to find this V, okay, from the formula V equals to negative integrate E dot dl, okay. And this E, okay, we will get it from the Gauss law, okay, Gauss law. All right, so according to the Gauss law, okay, so the total flux, okay, that is coming out from a surface will be equal to the total charge that is enclosed by the surface, okay. Since we are interested in the E, so over here we can modify it to be epsilon E, okay, epsilon E and ds. Okay, so this epsilon represent the dielectric properties of the material. Okay, if it is free space, it will be epsilon naught. Okay, so First thing, okay, we have to construct the Gaussian surface, right? So imagine now I want to find the electric field at this point. Okay, so I will construct a Gaussian surface. Okay, so this will be my Gaussian surface. So you imagine I'm having a Gaussian surface here. Okay, the green one. Okay, so this green one, this is my Gaussian surface. Okay, from the side view. Okay, 3D view. Okay, my Gaussian surface. Okay, so now you have to determine the directions of your electric field. Okay, by looking at the red color arrow over here. Okay, the red color arrow over here. Okay, you can see that the electric field, okay, is in the negative R directions. So in this case, I will pick the directions from the cylindrical coordinate. Okay, so this is from the cylindrical coordinate systems, because you look at the structure of these coaxial capacitors, it is in the cylindrical structure, so I pick cylindrical coordinate systems. Okay, so over here it will be integrate epsilon, so you write down the E in the negative R directions, and dot product with ds. Okay, so you can refer to the formula sheet that I share in the author. So the ds for the cylindrical coordinate systems, okay, is equals to the r, d phi, dz, and r directions. Okay, so this one represent the ds, okay, for the cylindrical coordinate system, and we are going to replace it here. So it would be r, dr, d phi, dz, okay, and also the r directions. Okay, so we are going to define the interval of these two terms. Okay, so for the phi represent the angle. Okay, so the angle of the angle of the rotations of the cylinder. Okay, so it will rotate, okay, 360. Okay, so it will be from 0 to 2 pi, and this dz represent the height. So let's say if the height over here, okay, the height over here is L, okay, for example L, I represent the length. Okay, so you will represent it from 0 to L. Okay, 0 to L. So you will do the integrations like usual. Okay, so you will get this one will become -1. Okay, so you integrate the phi, the epsilon, and E, you take out. You integrate the phi, you get 2 pi, and you integrate with respect to z, you get L. Get the length, and you have one more R here. Okay, R. So this is Q. So your E is equals to, and you have a -1 here, -1. Okay, so your E is equals to Q over 2 pi epsilon R L. Okay, and it is negative. So if I specify the directions, it will be R. Okay, so this one represents the direction, right? The directions. Okay, so now you get the E, and you are going to replace it here. You're going to replace it here. So your V is equals to negative E dot dl. Okay, so you put the term inside. So you have a Q over 2 pi epsilon R L. Okay, and in the R direction, you have a negative. Okay, dot with the dl. Okay, so this dl actually represent, okay, the length, okay, how far your electric field propagate, okay, and where your electric field propagate. Okay, so if you look at the top view here, the top view, so your electric field is from here over here, right? Okay, this is your directions. Okay, so let's say the inner conductors, okay, has a radius of A. Okay, and the outer conductor has the radius of B. Okay, so we will integrate from, okay, negative terminal, okay, to positive terminal. So this dl will be dr. Okay, follow the directions of the radius, and in the R directions, and it will integrate from A to B. Okay, so this A is a negative terminal, okay, and this B represent a positive terminal. Okay, you must always integrate from negative to positive. Okay, see, negative is here and positive is here. Okay, so the radius is from A to B. Okay, this one. Okay, so this one we can cancel it, this one we cancel it to become 1. So you take out all the constants, so 2 pi epsilon, you have L, right? So you just focus on the 1 over R, A to B, and dr. Okay, so when you integrate this one, you will get epsilon L ln, okay, ln R. Okay, so B and A. So you can write it as that Q, okay, over 2 pi epsilon L ln B minus ln A. So it can be write as ln B over A. Okay, so now this is your V equations. Okay, so after getting your E equations, you are going to replace it here. Okay, so the capacitance is equals to Q over V. So it's equals to Q multiply 2 pi epsilon L over Q ln B minus, over A. Okay, so you cancel this one. So the capacitance, okay, for a coaxial capacitor is equals to 2 pi epsilon L, okay, ln B over A. Okay, so the epsilon represent the material in between the inner and outer conductor, and this one represent the length. Okay, so in the PowerPoint it's not L, but it's a capital letter L, but both brings the same meaning, so it's the length. Okay, it's the length of the coaxial capacitors, and B is the radius of outer conductor. Okay, of outer conductor, and the A is the radius of inner conductor. Okay, radius of inner conductors. Okay, so this is the formulas for a coaxial capacitor.